Now let's look at the noise performance of conventional amplitude modulation, first with synchronous detection, and then later we will look at AM with peak detectors. We will use the same system setup when analyzing the noise performance. Here we have this will be now the amplitude modulated signal, and then we add the Gaussian white noise, and then the sum of the signal plus the noise is then applied to our receiver. The first part of the receiver is a bandpass filter, just as before, and then that's followed by the demodulator, which will have a detector followed by a low-pass filter. Here's our equation for the amplitude modulated signal. We've got an amplitude AC for the carrier, and then this term in square brackets, 1 plus m times x of t. M is the index of modulation. That tells us how deep the modulation is, how deep the amplitude modulation is. X of t is the message signal, and the restraints on these two terms, the absolute value of the message signal is plus and minus 1. So our message signal lies between -1 and +1, and the index of modulation is somewhere between 0 and 1. If we have an index of modulation greater than 1, then we are overmodulated, and that interferes with proper demodulation using a peak detector. So the constraint for the index of modulation is it's between 0 and 100%, or between 0 and 1. The additive noise is the noise that is passed through the input bandpass filter. So the received signal, the total received signal, is the AM signal plus the noise, and we've got an equation for the AM signal. And when we have we will look then also at the additive noise. So the input signal power is the AM signal squared and then time averaged. So we take the AM signal and we square each of the terms, and then we're going to time average. AC squared is simply AC squared, and then we have this term in brackets. Then when we square this, we get a 1 plus the cross term 2m x of t plus the m squared x squared term, and then that multiplies this cosine squared, which is 1/2 plus 1/2 cosine at twice the angle. So when we multiply this out, we're going to get 1, 2, 3, 4, 5, 6 different terms. Now, most of these, all of the terms that involve this cosine 2 pi times 2 fct term, they will all time average to 0. So we don't have to consider anything multiplied by this last term, because those would all time average to 0. So we now have a 1/2 distributed across these three terms. Now 1/2 times 1 times AC squared and then time averaged gives us this first term. And then we have a 1/2 times 2m times x of t. That will be time averaged, but x of t time averages to 0. So this cross term will time average to 0. And then the final term will be a 1/2. M is a constant, so m squared is a constant. So we have a 1/2 AC squared times m squared times x squared of t time averaged. And then with a little algebra, we can factor out 1/2 AC squared from these other two terms. And this now gives us the signal power into the demodulator. And it involves the amplitude of the AM signal. It also involves the index of modulation M and the power in the message signal as well. The noise power that is passed through the bandpass filter, as we've already determined, is N naught. That's the intensity, or the power spectral density of the Gaussian white noise is N naught over 2, and it's passed through a bandpass filter with bandwidth BR. So the total noise power is N naught times BR, and then since for double sideband, the receiver has to have a bandwidth of twice the bandwidth of the message signal. So now we have this expression 2 times N naught times B, input noise power. Now we form the signal to noise ratio at the input of the demodulator. In the top of the fraction, this is the signal power as we've just worked out, and the bottom of the fraction is the noise power. And you can do a little bit of algebra and simplify that expression. And you'll notice we've got an m squared involved in this. This is the index of modulation and the message signal power as well. This received signal is then going to be demodulated using synchronous detection first. So we take the received signal and we multiply by this replica of the carrier with an amplitude of 2, because that will cancel 1/2. That will come up later on. That's passed through a low-pass filter, and for conventional AM, we also have to block a DC component. So we have a DC block in this block diagram as well. The received signal is the AM signal plus the noise, and we're going to use for the noise, we're going to use this narrowband noise model, where we've broken the random noise into its in-phase component and its quadrature phase component. For amplitude modulation, the bandwidth of the bandpass filter must be 2 times B, so the noise power is 2 times N naught B, and as we determined in the double sideband signal example as well, the NC squared time averaged has also got to be 2 times N naught times B. So the total received signal is the AM signal. This is the first term is the AM signal, plus the noise signal is the second term. And the demodulation process will take this received signal, multiply it by this replica of the carrier, and then we'll pass it through a low-pass filter, and we'll look at it. So let's look at first what the result is to that point. So here is the AM signal plus the noise. So we have the AM term plus the cosine and the sine for the noise. That's all multiplied by this replica of the carrier. So we get a cosine times a cosine term, that's a cosine squared, and then a cosine times a cosine, a second cosine squared, then a cosine times a sine, so it gives us a sine times a cosine. After we apply the trig identities to each one of these, cosine squared trig identity, and then the sine times a cosine trig identity, then we have all of these different terms, 1, 2, 3, 4, 5, 6, as they're shown here. Sine 0 is 0, so that term is eliminated. The low-pass filter eliminates the terms with the cosine, and the sine as well, that are at twice the carrier frequency. So we are left with these first two terms in our equation. So the components that are passed by the low-pass filter, we have AC, and then this term in square brackets, 1 plus M times X of T, plus the noise component NC of T. Distribute the AC through this, you have AC times 1. Well, that's the DC term that will be blocked. So the term multiplied by 1 will be blocked by the DC block. So we have AC times M times X of T plus NC of T. And this now is the signal that comes out of the demodulator. We have a scaled version of the message signal that is scaled by AC times M. AC is the amplitude of the carrier. M is the index of modulation that goes between 0 and 1. And the value of M equals 0 means there was no modulation at all. So that takes out the message signal completely. And at most, the value of M will be equal to 1. The output signal power is AC squared M squared X squared time averaged. And the output noise power, NC squared time average, is equal to 2 times N naught times B. So we can form the signal to noise ratio at the output, AC squared M squared x squared t time average divided by 2 times m naught times b. So this now gives us an expression for the signal to noise ratio at the output of the synchronous demodulator operating on an AM signal. So now we're ready to look at the performance of this demodulator in terms of signal to noise ratios. So we take the signal to noise ratio at the output and compare that to the signal to noise ratio at the input. If you look back on the previous slides, in the top of the fraction we have the expression for the signal to noise ratio at the output, and then the bottom of the fraction is the expression for the signal to noise ratio at the input. And after everything cancels that can cancel, we are left with this expression, 2 times m squared x squared time average divided by 1 plus m squared x squared time averaged. Now, at best, the best we could possibly do, this term m squared is at, we'll set that equal to 1. That's the best we would be able to get. And if at best the product of m squared times the power in the message signal, that's got to be less than or equal to 1, since the range of the message signal is between -1 and +1. At best, this ratio is going to be 1, which is the same as we got for the double sideband. Okay, this slide is just doing some algebraic manipulation. I want to take the signal to noise ratio at the output, which is this expression in this yellow box, recalling that the signal power into the demodulator was given by this expression earlier, and with some algebraic manipulation involving multiplying and dividing by this common term and manipulating things around a bit, this expression relates the signal to noise ratio at the output of the synchronous demodulator with involving an expression with the signal power into the demodulator. So now I've got I can compare the signal to noise ratio of AM with synchronous detection to the signal to noise ratio of the baseband modulation system, which is what we're comparing things to. And so here's the signal to noise ratio for the AM divided by the signal to noise ratio for baseband, and after things cancel, we get this expression that involves is greatly dependent on the value of m and the message power x of t as well, x squared of t time averaged, I should say. Taking the same criteria, m squared times x squared of t times averaged has got to be less than or equal to 1. So at best, that's going to, we have a 1 divided by 1 plus 1, so that the signal to noise ratio of the AM system with synchronous detection is got to be less than 1/2 the signal to noise ratio at the baseband of the baseband system, which means that's 3 decibels worse than baseband. So built into the mathematics of amplitude modulation is a performance worse than baseband communication. You remember with double sideband, it was they were the same signal to noise ratios. So for double sideband, the modulated signal to noise ratio was equal to the baseband signal to noise ratio. With AM amplitude modulation, even with synchronous detection, it can never be as good as baseband. It's always going to be worse, which accounts for the static and the hiss that you invariably hear in an AM radio.